at? So we're back talking about section 1.6 and following up or finishing up the rational equations, the equations that have fractions in them. Sometimes these can be really tough ones. I feel like I wanted to reiterate how you find the LCD to eliminate the fractions. Again, this is section 1.6, the other types of equations. So kind of the difficult cases, I would say. For me, I think 1.6 may be one of the hardest sections in the whole book because it's just this hodgepodge of kind of difficult situations with equations. Most of the equations we solve in algebra are linear, x to the first, like you did in the earlier section, or they're quadratic, x to the second. We have a quadratic formula and methods to solve that. So this section takes in other things that might come up. So again, I think it can be kind of the tough situations or the ugly algebra situations. And so here we're going to share some strategies for cleaning these up and strategies for solving these. So when you have fractions in your equations, and here's some examples. This is the one on your handout, but before we do it, I want to show you some other examples, just how do you find the LCD. So basically, if it's algebraic fractions, you need one of each letter and where it's at the most. So you would need one of each of these. That would be the LCD. And so then we would times each side by ABC. A, B, and C. And this side would also, to keep the balance, be times by A, B, and C. Now the reason that works is when you distribute, you're multiplying when you distribute. So this is over 1. And then diagonally, these denominators where you just picked the least thing they'll all fit into, the LCD, these should go into that. It should cancel out all the denominators. So you'll have BC times 1. And then here, when you distribute, you'll need all those again. When you distribute, you go back to the full LCD. But this time, the B's cancel. And then you have AC times 1. And then lastly, the C's cancel. AB times 1, or times whatever's up there. But it gets rid of the fractions by timesing by the right LCD. Another example, before we do our one that's on our handout, another example, just thinking about how to find the LCD. So look at this one. You've got all kinds of letters there. Well, you're going to need an X and a Y and a Z. Like before, you need one of each letter and then where it's at the most. So you're going to need the X is to the third here. So it's going to take X to the third for everything to fit. You know, everything has to fit into it. So you need the biggest amount, the biggest exponent on any variable. So X to the third. Then you've got a Y. Well, here's Y to the second. You're going to need Y to the second. And then you've got a Z. So you're going to need a Z. You need the least thing. Every one of these has to fit into that evenly. And then you distribute that out. All right, now back to our problem at hand. So just kind of reiterating how to find those LCDs. And I can talk to you about LCDs all day long if you want to call me or meet on Collaborate to go over some more problems like that. But here's our next example. We're trying to figure out the least thing all these denominators will go into. It just so happens this last one will factor, and we should factor any that need to be broken down. Like, I know this isn't just an A and a B, but it's a quantity. Well, that has to stay together. You have to say, I'm going to need X minus 1 as a factor, and then this X plus 1 is a totally different factor. So you need one of each of those, just like they're different letters. So each one of those, well, it just so happens this last one will factor, or do the reverse of the FOIL method. If you FOILed it, that would be the X squared. The outer is minus 1x, inner plus 1x, and last is the minus 1. This foils to be that. Well, look, is exactly what we've got here. So that is also going to fit into the LCD of x minus 1, x plus 1, one of each thing. And here's how I know it works. Whenever I times it to each side, every one of these denominators fit. They have to fit. That's the least thing they all fit into. So whenever I distribute it here, notice whenever I'm multiplying, again, that's over 1, diagonally, the x minus 1s would cancel, again, because they're multiplied and diagonal matching factors can be canceled. You've got x plus 1 times minus 4x. I'm going to put minus 4x in front of it like that. Then I'll distribute it here. Notice, so no denominator, you know, no fraction. So when I distribute it here, you got to go back to the full LCD. When I multiply here, the x plus 1s cancel, and I have x minus 1 times 4, like so. No denominators. Then lastly, I'm multiplying here. This is over 1, this is that, so it's just a different form of it, and I'm multiplying exactly, both of those are exactly the same, so that fits into it or divides into it evenly. So it's just a 1 there. So you just have 1 times negative 8. So voila, no fractions, right? So this allows us then to have a more solvable, doable equation to solve. So do your steps we've been doing, you know, distributing, if you have to use the FOIL method, and then combine any like terms. Notice minus 4x and plus 4x cancels, so that's kind of nice. And then this minus 8 needs to come over and be minus 4 plus 8, which is 4. From there, it's a quadratic. This would be your A term. B is 0. There's no middle term, right? The B term has a coefficient of 0, so you don't see it. And then the C term, the constant, is 4. So you could plug it in the quadratic formula, always an option. But I could also clean this up a little bit, and I would divide by the negative 4. I kind of like for my squared term to have a positive coefficient. It's not a rule, but it makes it easier for me to kind of see how I'm going to factor it. So, and because I can here, those cancel to be 1x squared. 4 divided by negative 4 is negative 1. And then 0 divided by negative 4 is still 0. So it doesn't affect that right side. Now this is exactly that. You might notice we can go back up to that, and that will factor, or you could use the formula, but it's factorable to exactly what we saw before. And so that's going to factor, and then setting each factor equal to 0 is how we solve by factoring. It gives us 2 solutions. And daggone, they're exactly the 2 solutions that you cannot use in the original problem. And this kind of contrived problem to make a point that this could happen. It's kind of an odd thing to happen, but these are the 2 solutions we get from solving, and they're exactly the things you cannot use. Like if I try to plug in 1 into the original problem, if you remember right there, that said x minus 1. Well, 1 minus 1 makes a 0 denominator. That's undefined, and we know that's not allowed in math. So we can't use that answer, and you can't use the negative 1 here. Negative 1 plus 1 is 0. So both of those would cause, and they do it here as well, cause zeros in the denominator. So there's actually just no solution to that. It's an example with no solution. All right, so that's some examples of rational equations and how you can get into some sticky situations. Quadratics come back again, and some linears once you clean it up. All right, like I said, any of these, if you want more follow-up, always feel free to reach out and let me know if you want to talk further and do further examples. All right, next topic is work problems. So they saved this last type of reading problem for this section because it will involve algebraic fractions. So it kind of goes with the rational function topic. In a work problem, and follow along on your paper, it says work problems are solved similar to distance problems. Distance is equal to rate times time. Rate times time tells you how far you go. Work is similarly also rate times time. Tells you how much work you get done. How fast you work, your rate of work, and then how long you work. Rate times time are the 2 factors that tell you how much work you get done. One big difference, though, is we're going to set the addition of these 2 people are working side by side, and we want them to finish a job, to equal 1 completed job. So these are typically set equal to 1, unless you're trying to get 3/4 of the job done, which none of your homework will do that, or half the job done, or we could do other factoring amounts. But normally, we're trying to complete a job, so we set it equal to 1 complete job. So, for example, if it takes one person 5 hours to complete a job, their rate would be 1/5 job per hour, right? And that's a person that takes 5 hours to complete, whether it's mowing the grass, cleaning the house, some sort of job that you're paid by the hour. If it takes 5 hours of work and you worked to get it done, you work 1/5 of it, job per hour. So that's how we do rate of work, and then we times it by, say you work for 4 hours, you're going to have 4/5 of your work done. Does that make sense? You know, the rate is 1 over that times how long you work. Say it's 4, you'd get 4/5 of your work done. And that's generally how we do work problems. And you can see the format for 2 people working together. You have the one person, 1 over their individual time, like a 5-hour job they're doing, times the time they're working together. Then you add that to the other individual time, times how long they work together. And you're trying to equal how long does it take them to equal 1 complete job. So this is the formula or the format you're going to use to solve any work type of problem. So here we're doing a mowing the yard problem. So our example says it takes Mo 5 hours to mow the lawn. It takes Joe 6 hours to mow the lawn. So how long do you think it takes them together, right? If it takes your friend 5 hours and you 6 hours to do any type of job, whatever it is, say mowing the yard, how long do you think if you both start consistently working, how long to get done? Well, you know it's going to be less than 5 because Mo can do it by himself in 5 hours, and if you're helping, you should lighten the load and make it less. So considerably less time. Let's see. So the formula says do 1 over, there's Mo. We don't know how long together. That's the question here. So 1/5 times T. We usually don't put a big X though. We just say 1/5 T. The other person, Joe, takes 6 hours to mow the lawn, so that rate would be 1/6 times the time working together is what we're trying to figure out, equal to 1 job. So that's how we'll flow with the this type of problem. So this takes us to what we were doing earlier. We've got fraction problems. You want to times by the LCD. These T's are over 1, so they're on top. Actually, we could consider this 1 times T over 5 times 1, 5. T over 5. And then this would be T over 6. So the T's aren't part of the fraction there. You know, they're not in the denominator for the LCD. Only those numbers. So the LCD is just the 30. We're timesing both sides by 30. 30 times T over 5. It divides to be 6 times T, 6T. We use that 30 each time we distribute. So remember, it's still 30 when we distribute here. The 6 divides into that 5 times, and then 5 times T, 5T. And then 30 times 1 is 30. We can solve this. 6T and 5T is 11T. 11T equals 30. Divide by the 11. And the time that it takes the 2 people, Mo and Joe, to get the yard done working together, it's a little less than 3 hours. 30 over 11 would be, what, 2 hours and 8/11 of an hour, almost 3 hours. So a little less than 3 hours working together. And that's the preferable way we'd leave that answer, the more exact answer. All right, another example. Example 2, we're going to use this same formula for all this section. Just keep this in mind. This is how we work all the work problems. Sometimes you know the time together and you're asked to find the individual. This is what happens in example 2. It says one printer can do a job twice as fast as another. So working together, they can get the job done in 2 hours. So you see how I know the time together there, but I don't know the individual time. So it mixes this up a little bit. Figure out how long it takes each printer alone. So what we know is the individual time. One takes unknown X times the time together was 2 hours listed. The other printer is twice as fast, takes twice, not twice as fast, but it takes twice as long, times the time together equals 1. So again, we knew the time together, but we just had a clue about the individual times. One takes twice the other. So then the LCD here, remember these 2's are on top. So the only thing in the bottom is this X and 2X, and then nothing there, just 1. So 2X would do it. 2X is our LCD. So we times each side by 2X. 2X times 1 over X. The X's cancel. You've got 2 times 1. Oh, then times 2, making 4. Distribute the 2X here. When we distribute it here, look at this. The 2X's completely cancel, and you just got 1 times 2. And then lastly, 2X times 1 is 2X. So a linear equation to solve, which is 6 equals 2X. Divide by the 2. 3 is our answer. So it takes 3 hours. That's the individual time of the quicker printer, 3 hours working alone. And that one's twice that, so it would be 6 if asked for each time. All right, so that would be an example of using the work problems. All right, I'll come back in the next video to the next type of equation.